In this lecture, we are going to learn about bitwise operators in C. Now, bitwise operators performs the operation bit by bit. That means the operand will be converted into the sequence of binary digits, that is a bit, and then the operation is performed on bits, not on the number directly. Now, there are different types of bitwise operators. The first one is bitwise AND, represented by ampersand, bitwise OR, represented by a single bar, bitwise XOR, exclusive OR, also called as XOR, represented by a cap like this, bitwise NOT, represented by a tilde like this is called as a tilde, and left shift, represented by less than symbol twice, this is left shift, and right shift is represented by greater than symbol 2 times like this. So these are the 6 different types of bitwise operators. Out of all these 6 operators, bitwise NOT is a unary operator, and all other operators are binary operators, meaning they will have 2 operands. Now let's take an example of bitwise AND. It takes 2 operand because it's a binary operator. So let's say the operands are OP1 is the first operand and OP2 is the second operand. Whenever you are performing bitwise operation, these operands should always be integer numbers. Always the operands must be integer numbers. It can be either signed or unsigned, meaning signed integer is allowed, unsigned integer is allowed, even character is allowed because character can be represented as an integer, long is allowed, short is allowed, double and float is not allowed as an operand in the bitwise operator. All of these operators will only allow or only work with the integer operands. Now let's look at these operands in details here, okay, how it works. Now the first one here is a bitwise AND. So let's look at the truth table of bitwise AND because it is working bit by bit level. So 2 inputs of this binary bitwise AND are given here as input 1 and input 2. So in bitwise AND works as your logical AND, but the difference is that the input for bitwise AND is a bit and not a number directly. Now let's see what will be the output of bitwise AND. Now bitwise AND will have 1 in the output if both the inputs are 1. So if both the input bits are 1, the output is 1. In all other cases, the output is 0. This is as good as your AND gate. Okay. Now how does bitwise OR, that is 1 vertical bar, works? Now in bitwise OR, the output is 1 if any one of the input is 1. Okay, so in this case both the inputs are 0, so output is 0. In all other cases output is 1 because one of the input in all of these 3 cases are 1. Okay, now let's look at bitwise exclusive OR. Now exclusive OR is something new here, right? Now in this case the output is 1 if both the inputs are different, right? So the output is 1 if the inputs are different. Now let's look at this here. Both the inputs are 0, so output is also 0. Okay, here both the inputs are different. See, the first input is 0 and the second input is 1, so they are different, therefore the output is 1. Okay, similarly in the third case, this is 1 and this is 0, they are different, therefore the output is 1. And in the last case, the input bits are same, right? 1 and 1, so therefore it is 0 as output. Okay, this is the truth table for bitwise AND, bitwise OR and bitwise XOR, also called as XOR or exclusive OR. Now let's look at bitwise AND in more details. The symbol is this one, bitwise AND. Now here this is the truth table of bitwise AND. Let's look at this particular code snippet wherein we have declared one character A, which is 2, and B is 5. We can always store an integer number in a character variable because character is internally represented as an integer number, right? A is 2, B is 5, and I want C to be as A and B. So first of all, what happens is, whenever this is executed, first of all A would be converted into its binary form. Because A is a character will take 8 bits in the memory. So A will first be converted into 8 bits binary sequence. So the sequence for A, that is 2, A is 2 in decimal. 2 in decimal is 0, 0, 0, 0, 0, 0, 1, 0 in binary. So this conversion is done first. Then B is also converted in binary, that is 5 is converted in binary, which is given here. And now if I try to perform the AND operation on this, what happens is I'll have to get the output here and it will be treating bit by bit. Okay, so first this bit at units place, they will be considered. So the inputs are 0 and 1. Whenever the input is 0 and 1, output is 0, 1 and 0. So this is treated with this one. Okay, input 1 and input 2. Whenever the input is 1 and 0, again output is 0, right? So therefore here also 0, 0. Whenever both the inputs are 0, output is 0, 0, 0 and 0. So you see all the bits of the output is 0. That means if you convert this into decimal, this will be decimal 0. So the output of this entire thing is 0. That means C will be assigned the value 0. So finally the variable C will be having the decimal value 0. This is how bitwise AND works. Now here, if this was in case of bitwise, if I was doing this as the logical AND, what would happen was A and B, right? The output would be something different because A is a number which is a non-zero number. So non-zero number A is 2 and B is 5, right? Both are non-zero numbers. So non-zero number is treated as true. This is also true. So in logical AND, if both the inputs are true, output is true. Therefore C will be also true. In that case, C would be storing the value 1. So this is how logical AND works and this is how bitwise AND works. There's a difference. Okay. Now let's move on to bitwise OR. Now the example is given here. Okay, the code is given here. A is 2, B is 5, character is C, and I would like to store A bitwise OR B. Okay, this is the symbol for bitwise OR, vertical bar, only one time. Okay, now let's see what is the output. If I try to apply bitwise OR here, it will be treated bit by bit. So this will be treated with this one, this with this one, this with this one, this with this one, this one, this one, this one and this one. Okay, the first input is 0, second input is 1, so the output is 1. Looking at the truth table, right, if any of the input is 1, the output is 1. Here it's 1, here 0, 0, 0, 0, 0, and this is how you get the answer. And if you try to convert this in terms of decimal, after the operation is done, it will be converted into decimal by the compiler. So if this is converted into decimal, it happens to be decimal number 7. So finally 7 is stored in the variable C, and if you display C, it will give you the answer as 7. This is how bitwise OR works. Now let's look at bitwise XOR. Okay, now bitwise XOR or exclusive OR is having the symbol as a cap like this. Okay, now in bitwise OR, the output is 1 if the inputs are different. So in this case the inputs are different, 0 and 1 are different, so output is 1. Here the input is different, so the output is 1. Okay, in all other cases output is 0. So let's try to apply cap here. Okay, so 0 and 1, so inputs are different, they are different, so it is 1, different, so it is 1, different, so it is 1, and they are same, 0, same, 0, so 0, 0, 0, they are same, so it's 0. So if you look at this, this is 0, 0, 0, 0, 0, 1, 1, 1. If you convert this into decimal, it will be decimal 7, and finally C would be holding the value 7. This is bitwise XOR. This is how it works. Now let's look at bitwise NOT. Now bitwise NOT is also called as bitwise complement. Okay, bitwise complement because it will give you the complement as the output. So if the input is 0, complement of 0 is 1, 1 is the output. If the input is 1, 0 is the output. Okay, in any bitwise operator we will not deal it as true or false. We will talk in terms of 0, bit 0 and bit 1. Now here I am trying to perform the complement of A complement. So A is 2, right, and binary representation of 2 is given here. So what is the complement of A? What is complement of 2 is you have to just flip the bits. If it is 1, make it 0. If it is 0, make it 1. So this is 0, it becomes 1, 1 becomes 0, 0 becomes 1, 1 becomes 0. Okay, so all this 0 will become 1, 1, 1, 1. So this is the output, right? This is what you get in terms of binary. Now let's try to convert this in decimal. Before we convert, let's see what is the type of character. Character is internally is the signed character, so it's a signed integer. Internally it's a signed integer, right? So if it's a signed integer, it can also hold the negative numbers. And if you look at this number very closely, this is starting with 1, so therefore it must be a negative number. Okay, now what would be the value for this entire sequence of binary digits? Let's try to find this out. As you know that negative numbers are represented using the 2's complement notation, let's try to find the 2's complement of this sequence. So what is the 2's complement of 1 1 1 1 1 1 0 1? It is simple. It is the 1's complement of 1 1 1 1 1 1 0 1 plus 1. Okay, so what is the 1's complement of this one? 1's complement is as good as doing bitwise NOT, that is you flip the bits. It will be 0 0 0 0 0 0 1 0. Here I have just converted 0 to 1 and 1 to 0, and I add 1 to this. So I am trying to find the 2's complement of this entire sequence, and if I add this, 0 plus 1 is 1, 1 and 1, 2, 3, 4, 5, 6 zeros, right? So this is the 2's complement of this number, right? Now this is a positive number and I know that this is number plus 3. So if this is plus 3, this has to be minus 3, because we know that 2's complement of plus 3 is equals to minus 3, or we can also write 2's complement of minus 3 is also equals to plus 3. Okay, so this is as good as minus 3. That means if I do bitwise NOT or bitwise complement of 2, I'll get minus 3 as the output. Okay, this is how it works. I hope you have understood how bitwise NOT operator works. Now let's move on to left shift. Now left shift, the symbol is less than symbol 2 times. Okay, here I am taken a character A which is assigned the value 5, and 5 in binary is represented here like this. Okay, now look at the syntax for left shift. It has 2 operands. So this is the number. This should always be an integer number. All the operands must be integer. This is a number that must be shifted towards left. Number to be shifted. This is the number to be shifted, that is 5 in our case. And this is by how many positions it needs to be shifted. By how many positions. So what I'm trying to do here is I'm trying to shift 5 towards left by 1 position. By 1 position. So I try to shift all the bits to the 1 position towards left. Okay, because this is a left shift. So if I shift this towards left, this will be lost. Okay, there is no place to store this because my character is only be able to hold 8 bits. So this 0 will come here. This 0 shifts here. All these numbers will be shifted. All these bits will be shifted towards left. Okay, this is 0 and this is 1. Now you see there is an empty space created at the rightmost bit, that is this significant bit is lost here, it is not there. So in this case you will have to append, or you need to add 0 here. Okay, so this is my final answer. And if you try to convert this in decimal, it will be 1010 is 10, that is plus 10. So if you try to shift 5 towards left by 1 position, you will get the answer as 10. Okay, so shifting left is also as good as multiplying by power of 2. Now let me explain this. Okay, how it works. So I was trying to shift 5 towards left. Okay, so I can predict the answer as, so to predict the answer I'll write 5 times 2 to the power something here, right? So how did I get this 5? 5 is nothing but my A, the number that I want to shift. 2 because it will work with the power of 2. Right, and what would be in the exponent is this position. By how many positions I have shifted? 1 position, right? So if you just do this calculation, it will be 5 times 2, which is equals to 10, which is our answer. So technically, whenever you are doing left shift, it is as good as multiplying by the power of 2. Okay, so this is how it works. Now let's look at the last operator, that is the right shift operator. Right shift operator, the symbol is greater than symbol 2 times. Okay, here the same example, A is taken to be 5 and I would like to do the right shift of A. So I would like to shift A. A is represented in binary here towards right by 1 position. By 1 position. So I would like to shift it right by 1 position. So if I shift right, what happens is this, if I shift this towards right, it will come here. 0, this 0 will be shifted here. This 0 will be shifted here, this 0 will be shifted here, this 0 will be shifted here, this 1 will be shifted here, this 0 will be shifted here, and this 1 is actually lost. It is removed totally, and there is a space available here at the most significant bit. This is left empty. Now what digit do I place here? Do I place 1 or 0? Right? So if the input number happens to be negative, if it is a negative number, then you have to place 1. Okay, 1 for negative. If it is a positive number, you have to place 0. Input 5 is positive, so I'll have to place 0 here. So this is 0 is placed here. If you look at this, the answer is 0 0 0 0 0 0 1 0. So 1 0 is nothing but 2 in decimal. Now this can be also written as right shift is as good as dividing by power of 2. Okay, let me explain how it works. Okay, now I can predict the answer. I was shifting 5 because A is 5. I was trying to do 5 right shift 1 by 1 position. Now I can predict the answer here. So how do I predict the answer? The 5 is the number that I would like to right shift. By how many positions? 2 to the power. I have to give the position. How many positions? Here 1 position. So I'll write 1. So this is as good as writing 5 by 2. And if you divide 5 by 2, right, 2 times 2 is 4 and the remainder is 1. So the quotient is 2 because this is integer division. So 2 is the quotient, which is my answer. So right shift is as good as dividing the number by power of 2. Okay, and one very important point to note is that whenever you are shifting towards right, the empty space that is generated at the leftmost bit would be 0 if the number is positive, and this should be 1 if the number is negative. Okay, this is the point that you should note. So I hope you have understood the working of all these 6 bitwise operators. Now you may be wondering what would be the application of these operators, where we can use them. Right? So that I'll be covering in my next lecture, wherein I'll be discussing some of the applications of bitwise operators. Until then, stay tuned.